Okay, we're back for part 2 of 6.3 disc and washer method. Example number 3, we're going to sketch y equals the square root of x. This one, we're going to sketch x equals 0 and x equals 4. So I think what they wanted to say was y equals 0, because x equals 0 doesn't give you a region. And this was the region that they also had done, but I think that would have made more sense. So if you want to change that to y equals 0, I'm okay with that, but whatever. We're talking about that region, and we're revolving it about the x-axis. And so our representative rectangle, perpendicular to our axis of rotation, is going to have a width along the x-axis. That's a delta x. We know then that our integration is going to be in terms of x. I'm going to pick a point on the function there and imagine that this is x, y, so that this is the y value. And our y is the square root of x. So now our radius here is the square root of x, because remember that this is like a end of a bullet is what you'll end up seeing. So it'll end up being something like that where, you know, it's rounded. It's a rounded region because we're spinning it. So this representative rectangle is the little, like if I just sliced it right here, that bullet, this piece right here is the representative rectangle, and this right here would be that R. And so delta x is the height. So pi r squared times the height. So our volume, and we said it was in terms of x, so this is going from 0 to 4 in terms of x. Pi r squared times the height. So pi square root of x squared times the height. So I bring my pi in front, integrate from 0 to 4. My square root and my square go away, so it's just x dx. So pi, and now we integrate 1/2 x squared from 0 to 4. So pi would be 1/2 4 squared minus 1/2 0 squared, which that would just give you 0, so we don't need to worry about it. And 16 divided by 2 is 8, so this is 8 pi units cubed for your volume. Okay, example number 4. And by the way, we don't have a geometry formula that we can check that with. So now we're getting into the ones that are not able to be checked. Okay, so we've got y equals x squared. There's our y equals x squared. And we're going to revolve it about the y-axis. And it says from 0 to 4. So what I did is I just added the function y equals 4 here. And I looked at it as just this region spinning, okay? Even though, you know, because if you spin just the first quadrant, you're going to get the same thing as if you spin the whole thing. So we're just going to focus on that, on the first quadrant piece. And since we're spinning it about the y-axis, our representative rectangle perpendicular to the axis of rotation is this way, and if I look at the width of it, it's along the y-axis. That's going to be delta y. So I know I've got y integration. If I picked a point on my function, this would be the x of my point. Imagine going x, y, right? So this is the x of your point. So your y equals x squared, we want to solve for x. So your radius is the square root of y. And we knew we wanted y integration, so that works out great. So volume equals integration. We're going along the y-axis from y equals 0 here to y equals 4. Pi square root of y squared dy. And so bring your pi out front. Goodness. And integration from 0 to 4, square root and the square go away, y dy. So pi, this is going to be 1/2 y squared from 0 to 4. So 1/2 4 squared minus 1/2 0 squared, so we don't have to worry about that. So this also is going to give me 8 pi units cubed. Now on this particular one, this bullet type thing from, x equals 0 to x equals 4 is going to be the same as the bullet type thing from y equals 0 to y equals 4. So you end up with that same volume. So next one, y equals e to the x. So I'm going to sketch e to the x. I know that's 1. And from 0 to 2, so I'm just going to say, okay, here's my 2. So this would be my 1, whatever. I think, like in our book, if they wanted us to know this region, they would have said bounded by y equals e to the x equals 2, and the x and y axes, or they would have said x equals 1 and y equals 1. But they're talking about this region, though. I just don't think that these notes give a real good idea of what the region is. So if you were doing a different problem, like in a book or something, they're better about stating the region, although they're not perfect. We are revolving it about the x-axis, so perpendicular to your axis of rotation is my representative rectangle. I notice that it is delta x here, so I know my integration is going to be in terms of x. I'm going to pick my point on my function. It is an xy point, and so I imagine x, y like that, so I know this is the y, and it's already solved for y. So my radius is e to the x, whatever that y is. So my radius is e to the x. Again, you are, imagining that this spun about the x-axis, it kind of looks something like that. It's going to end up being that figure. So if I just took a slice of it right here, that slice is this cylinder. I just sliced it, and I'm using that one little sample space, sample cylinder, and this was my R, and this is my R. So I use that sample cylinder, this is my delta X, and I'm finding the volume of that, and then that's going to be, when we integrate, we're going to be adding up infinitely many of these. Some of them are going to be smaller down here. Some of them are going to be bigger down here, but the integration takes care of it for us. So pi r squared times the height. Pi, we said our r was e to the x squared, and we said our height was delta x. And when we put it into our volume, it's going to be dx. So volume equals integration. This is x integration, so we'll go from 0 to 2. Pi e to the x squared dx. So we'll bring our pi out in front. Integration 0 to 2, e to the 2x dx. And if we were taking the derivative of this, it would be 2e to the 2x. But if we're integrating, it's going to be e to the 2x divided by 2 from 0 to 2. So I'm just going to bring that pi over 2 out. And then this is e to the 2 times 2 minus e to the 0 times 2. Now be careful on that one, because when you put your 0 in, it did not make it go away. It actually gave you a piece of the function. And so this is our final answer for the volume of that figure. Okay, so that's the end of the disk method. Those are all the things where if you spin it, there's, it's an actual solid piece of three-dimensional something. The washer method, what ends up happening is when you spin it, part of it has a hole. So instead of having a disc, you end up having like a donut, which looks like a washer, like this picture right here, okay? And so I made up a little problem for this one just to kind of walk you through what the washer method is. So I made up the problem taking the region y equals x squared plus 1 and y equals 4 and spinning it about the x-axis. Okay, so if I was sketching y equals x squared plus 1 and y equals 4, and of course, we probably would have said and the y-axis, that region also, and then this would have been what we're going to spin about the x-axis. So notice there will be a hole here. Like there's going to be, a hole right here. This part over here, like, and it's going to be connected here circularly, but, so it's going to end up being this, almost like a donut, like it's going to be rounded like that, rounded, but it's going to have a hole. So we want to find the volume of that. So it's going to involve a little r and it's going to involve a big R. I don't know if I said it, but look, my representative rectangle for my little r is perpendicular to my axis of rotation. My representative rectangle for my big R is perpendicular to the axis of rotation. Both of them have a width of delta x along the x-axis, so I know I'm going to be having x integration. And so, since this is kind of a made-up problem for me, I have to put my work, kind of going down the side page, and you might want to do that too. So, to find the volume here, we're going to say that our volume integration from 0 to, now I have to figure out what this point of intersection is. So to figure out that point of intersection, I'm going to set my x squared plus 1 equal to my 4. And so I'd subtract 1 and then take the square root. So plus or minus the square root of 3, we know that this one is positive square root of 3. So we're going from 0 to positive square root of 3. We're going to do pi big R squared minus pi little r squared dx. So if you look here, my big R is 4, and my little r is going to be found by imagining a point on x squared plus 1. It's an xy point, and I can see it's the y of that point. So that's going to be x squared plus 1. So my little r is going to be x squared plus 1. My big R is just a constant 4. No matter where I put it between 0 and square root of 3, it's always going to be 4. So this is going to be, this is going to be 4 squared minus pi x squared plus 1 squared dx. I can factor my pi out, and this would be 16 minus x to the 4th plus 2x squared plus 1 dx. And then we're going to distribute the negative, and 16 minus 1 is 15. And distribute that negative to the other two. So now, integrate. 15x minus 1/5 x to the 5th minus, this would be 2/3 x to the 3rd from 0 to the square root of 3. So 15 times the square root of 3 minus 1/5 times square root of 3 to the 5th minus 2/3 times square root of 3 to the 3rd, and then minus all of those with a 0 would give me 0. When I take square root of 3 times itself 5 times, I get 9 root 3, then over 5. When I take square root of 3 times itself 3 times, I get 3 root 3. The 3's are going to cancel, leaving me with 2 root 3. 15 root 3 minus 2 root 3 is 13 root 3. And if I wanted to find a common denominator so that it's all over 5, this is going to give me, in the end, 56 root 3 after I found a common denominator and added like terms. So I've got 56 root 3 over 5 pi units cubed. Okay? So again, you're just pi big R squared minus pi little r squared there. And it creates a donut type situation. So now example number 6, find the volume of the solid formed by the region bounded by graphs of y equals the square root of x and y equals x squared. And so we are talking about this region right here, and we want to go about the y-axis. So you can see that there's going to be a hole here when you get this three-dimensional figure going, right? There's going to be a hole because you're imagining that this will spin, 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 spin. And so your little r from the axis of rotation to your first point, that's your little r, and your big R is from your axis of rotation to the end, and that's your big R. So if you're imagining that those are rectangles, they both have a width of delta y, so we know we're doing y integration. This is the x of y equals the square root of x, so I'm going to have to square both sides to solve for x. And so our little r is y squared. This point right here is the x of y equals x squared. And so I'd square root, and x equals the square root of y, so our big R is the square root of y. So now, volume equals, so this is integration along the y, so I have to know what this point of intersection is because I need to go from 0 to whatever this point is where they intersect. And so I'm going to set my square root of x equal to my x squared. Well, I got to get rid of that square root. So x equals x to the 4th, and then I move that over. And then I factor. And then I use my zero product property. And I see that they intersect at x equals 0 and x equals 1. Well, that's down here. So I have to put it back into the function to find out what the y is, and I see that the y is also 1. So I will be integrating on the y from 0 to 1. And it's going to be pi big R squared, which we said was the square root of y, minus pi little r squared, y squared, squared, dy. Bring out the pi. Square root and the square go away. And we end up with y minus y to the 4th as our integration. Oops. And so, integrating 1/2 y squared minus 1/5 y to the 5th from 0 to 1. And so when I put a 1 in, I just get 1/2 minus 1/5. When I put 0 in, it gives me 0. When I find my common denominator of 10, I get 3. So 3 pi over 10 units cubed for that really different looking figure, okay? But that is your volume, and you had to use washer method because it gave you a whole. So example number 7, find the volume of a solid generated when the region between the graph of y equals 1/2 plus x squared. So imagine that if this was 1, your 1/2 plus x squared goes like that, okay? Because it's just shifted up 1/2 unit. And then y equals x. So you're imagining that, let's say this is your 1. Well, 1, 1 is here. For 1 on this function, you actually are at 1.5. So I just wanted to show you how this actually is all below that other function. This is your g of x equals x, or your y equals x. And this is your f of x equals 1/2 plus x squared. And then I know my graph isn't going to look the greatest because when I put 2 in, it's going to be way up here, but we'll just imagine that they are talking about this region here, and you know, they're also got x equals 0. But that is the region that they're talking about. That weird region right there, and they want us to spin it about the x-axis. So I'm spinning it about the x-axis so I can see that there will be a hole when we spin it. So I'm going to say from my axis of rotation to the first part of what I'm spinning is my little r, and from my axis of rotation to the second part is going to be my big R. And, you know, if you want to make it like we've been making it so you can see that it actually has a little bit of a width there, this is going to be along the x-axis, right? So it's a delta x. So I know my volume equation is going to be integrating with respect to x. And now we have to figure out what our big R and our little r are. So our little r, if I put a point right here, I can see that that is the y value of my point, and that's just x. So my little r is x, because that's what my y is. My y equals x. And then here you can see that if I was going to that point on the function, I would go x, y. Again, that would be the y of my function there, which would be 1/2 plus x squared. So that would be my big R. So, you know, when you're spinning it and you have, you know, your slice is like a donut. And so we're going to be integrating along the x-axis from 0 to 2, pi big R squared minus pi little r squared dx. I'm going to bring the pi out. I'm going to, oops, I forgot my square there. I'm going to square 1/2 times 1/2 is 1/4, and then I've got a half x squared and another half x squared, just gives me a whole x squared, and then plus x to the 4th minus, and then this would just be x squared dx. And so you can see that your positive x squared and your negative x squared go away. So this is pi times the integration from 0 to 2 of 1/4, oops, sorry, I accidentally wrote x, 1/4 plus x to the 4th dx. So now, integrate. Now we have 1/4 x plus 1/5 x to the 5th from 0 to 2. And now if we put our 2 in, 1/4 times 2 plus 1/5 times 2 to the 5th. And then minus, put a 0 in, you get 0. So this becomes 1/2 plus 32/5. And if I found a common denominator and added my values, I get 69/10. So my final answer, 69 pi over 10 units cubed.